Hi all, this is Professor Won-do Chang of Bugyeong National University of South Korea. And today I will talk about EEG, especially for AI students. So if you are majoring AI and you want to do some research using EEG, then this video is going to be helpful for you. Today, this is a very short video of maybe 25 minutes or 30 minutes. Then I cannot cover everything about EEG, but it's about the basics of EEG. So I will talk the basic concept of EEG and how to measure EEG, the method we can measure, and I will talk about some algorithms and also the applications. First of all, so we can see the terminology. So this terminology is the electroencephalogram. This is we just shortly say EEG, and this means electro means electric things, and en means in, and cephalo means brain, and gram is our records. So in short, EEG is brain activities. So not just brain activities, but it is recorded signal of brain activities. Okay. EEG, there are many activities inside of our brains, and it generates potential changes. So when we try to measure out from outside of our brain, then that is the EEG what we are talking about. Maybe you have been watching this TV series, Dr. Brain. This is one of a famous Korean TV series. Maybe it's a bit old now, but I watched it. No, I just read a book, comic book. It's a webtoon. I didn't watch the TV series yet, but it is very interesting because this guy is trying to read someone's memories, not from the alive person, but from the dead person. So, because we can think that we know that our memories are recorded in our brain, and maybe it is possible to read someone's memory after his or her death. So, to read the memory of a person, then he wears a specific device, and it looks like EEG. So EEG device, EEG recording device. So he tried to connect using this device. He tried to connect to the other persons, other dead persons' brain, and then trying to read the brain activities directly. Okay, but yeah, so maybe it is possible in future, but now it is not possible yet. So this is the signal of EEG, our brain signals. Okay, so let's talk about the brain first. So everybody knows where our brain is. So it's inside of our head. And this is an organ that serves as a center of the nerve system. So when our when our brain have damaged, then our body is difficult to control our bodies, other bodies. So our brain is controlling so many things in our bodies. There are some organs working without brain signal, but like a heart. But yeah, most of our bodies are working under the control of our brain. Okay, and our brain sends signals to other organs to control, and each part of our brains are known as working parallelly. So there are so many neurons inside of it, and then the activities of the brain is not fully known to human being yet, but we know that this is working parallelly. So some part, for example, when you are watching this video, when you are watching my video, then you are listening my voice, and also you are watching, and then you are reading some text parallelly. So this is possible because our brain works parallelly. Okay, and our brain can be divided into several parts. So and each part have a name: frontal lobe, and temporal lobe, brainstem, and occipital lobe, and cerebellum. And these parts are working, has roles of different purpose. So we have so many person in this on this earth, and then there are, of course, our brains are all different, but the most of the people has the similar functionality. And basically, so most people's brain has similar functional structures. For example, our frontal lobes are in charge of movements and thinking, initiation, reasoning, behavior, memory, speaking, and if you are watching something, then your back lobe, the occipital lobes, are working hard to understand the visual stimulus, visual things. So some parts are in charge of language, and some parts are in charge of reading something. So it's all different. How do we know this? So because of a long-term history, long-term study about our brain, some researchers found a patient who were injured this part, temporal lobe, and then the doctor found that patients who injured on his temporal lobe, then he has some problems on his language skills. Then, so 1 case, 2 cases, 3 cases. Then finally, now we know that, okay, this part, temporal lobe, are in charge of languages. Okay. And physical structures of brain of human beings are almost the same for the most of people. Maybe there are some exceptions, but basically they are all the same. And even the functionalities, general functionalities of brain parts are also the same for the most of people. This is also known, but detailed functionality of brain could be different individually. And also, our brains could work differently. For example, if a person's brain of occipital lobe has some kind of problem from the childhood of a person, then this part is not used, and then cannot be used because there's some damages or something. And then another parts, like for example the frontal lobes or temporal lobe, and those parts are working for vision, for processing the vision information. So this is also possible. So that's why the detailed functionality of the brain could be different individually, but in general functionality of brain parts are very similar. Okay, and then I told you that our brain activities generate signals. And if you look inside of our brain, then you can find some neurons. And neurons looks like this, and soma, and then synapse, and axon, and etc. and the informations are transmitted through the neurons to conduct the specific task. So, for example, if you try to understand my English and try to understand my lecture, then your brain is working dynamically and sending signals here and there, trying to understand the language and my pronunciation and so on, and trying to process. And sending signals here and there is going to be very busy. So here, what I want to say is the signal is transmitted through the neurons. It's not just transmitted, but it's it could be emphasized, magnified, or it could be reduced, or it could be changed. It could be mixed. So that's how our brain signals transmitted inside our brain. And actually this happens not only in your brain but also in your whole body. Actually, it's when our body moves. When our body moves, then there is going to be some chemical changes in our body, and that chemical changes generates the electric signals, electric potential changes. Okay, and if we record the signal from our body, our muscle, then it's going to be the EMG, electromyogram. If we record the signal around the eyes, it's going to be EOG. So it's electrooculogram, right? So electrooculogram, in short, is EOG. And if you measure the signal around our hearts, then it's going to be called electrocardiogram, ECG. So that's what we are talking about. Okay. Do you know how many signals, how many neurons in your brain? So we can't sure exactly, but it's scientists say that we have almost 86 billion neurons in your brain in average. Yeah, maybe some of your brain have more neurons, and some of other person's brain maybe have less neurons, but in average 86 billion. So this means there are going to be 86 billion signals from your brain. So it's a very, very complicated signal. So let me compare this signal to our hearts. Our hearts are generating ECG, electrocardiogram, and this is pretty simple because this is ECG is just a heart movement. There is only one heart. Yeah, of course there are some. We can divide the heart into parts, several parts, but it's not more than 10. We have just around 8 parts and 8 parts of the muscles of our heart, and then it's going to be pretty simple. Let's think about the EOG. We have only 2 sources, left eye and right eye. And even these 2 eyes are almost moving together. So this is pretty simple. But this EEG is something different. 86 billion, not just 86. 86 is pretty much actually, but it's 86 billion signals. So, and these signals, this signal EEG is continuously generated in a real time because your brain never stops. It's continuously working and doing some activities, even during your sleeping time. Yes, you are dreaming, right? And then your brain is working. And also you need to control your body while you are sleeping as well. Okay, that was the brain. And let's talk about how we can measure our brain activities. First, we need to talk how to measure electric potentials in general. So we can measure electric charge between 2 points. And you may know this kind of devices, right? And we can measure, this is called multimeter, and using this multimeter we can measure voltage between two spots. Okay, we can say this is an electric charge between two spots. Okay, this is not difficult. This is not a difficult technique, but we can measure with cheap devices. So it is okay, but here I want to emphasize that we need two electrodes to measure the difference of electric charges between two spots. If I just put one electrode, use one electrode, then I cannot measure anything. Okay. Of course, there are electric charges there are electric fields in this air, but this is very, very difficult to measure electromagnetic field in the air. But instead that we can measure, it is relatively easier to measure the electric potentials changes. The electric charges difference between two spots. Okay. Then we can measure our EEG, our brain activities directly from a neuron. If there is a neuron, then if I put one electrode to the neuron's left side and the other electrode to the neuron's right side, I can put two electrodes like this, and then we can measure easily then what happens in that neuron. But it is very, very difficult because we have 86 billion neurons. So if you want to measure all the neurons activities, probably you need 86 billion electrodes and then lots of amplifiers as well. So it's difficult. And also, these neurons are too small. So it is difficult to measure, to put your electrodes directly onto the neuron. And also, the third reason is some neurons are deep inside of our brain. So there are neurons on the cortex, your brain cortex. So this is pretty outside of the brain, but some neurons are very deep inside of your brain. So in that case, it's going to be really difficult to measure the signal directly from the spot. So instead, generally we measure brain activities from outside of our skins. So we put lots of electrodes like this. Okay, lots of electrodes, and then we put it and then trying to measure the signals. So you can you see this multimeter, but we are not going to use this multimeter anymore. So we will use another one. But before talking about that, so let me talk about the difficulty of recording EEG more, because I told you that there are so many neurons generating signals, and then we are trying to measure the signal from the outside of brain, outside of our skull. And this skull blocks lots of signals. Our brain activities actually is very, very small. It's in microvolts unit. When you turn on the light, this is pretty light, and then this this light use 220 volts. And then when you are using your device, electric device like a cell phone, and then that use 5 volts, right? But our body use the electric signals inside, but that signal is very, very small. Yeah, especially our brain signal is less smaller than our heart signals and our muscle signals and etc. So it's in microvolt unit. So these weak signals are easily corrupted, distorted by the skulls. So I can give you this kind of image. So here you see that lots of people start talking each other, and you are trying to listen what they are talking from the outside of the house. And then you think this is an easy job? No, never. So if you try to understand somebody's talking of your next door, then it's the sound is very changed. Yeah, sound is going to be changed, and it's going to be mixed because there are so many people are talking together. So it's really, really difficult. So if you want to listen, if we want to record our brain activities really precisely, then you need to get rid of this car. And then you can put some electrodes here, and then you can record our brain activity. Then, yes, you can get more precise and accurate signals directly. But of course, if you have some trouble in your brain, then you want to do some surgery, then yes, you will agree to open your brain. But in general, if you are healthy and have no disease, and if you just use what you want is just to control something with your brain, and then yes, you will not accept to open your brain skulls, right? So this is not going to be happen normally, but sometimes it is necessary. So what I'm talking about now is reading EEG is really difficult. So let's talk about EEG more. Okay, now I'm continuously talking about the electrodes, and this is these are the electrodes here. The electrodes is the parts to put on our skins and to record the brain activities, or we can also use these signals to record the other activities of our bodies, but here let me just talk about the EEG. And to record EEG, maybe some devices use only 2 channels of electrodes, but if you are doing some research, in most of the case, probably you will use the 16 or 32 channels. Okay, but it takes so much time to put 32 electrodes on your brain. So EEG cap, electroencephalogram cap, is used to get the positions easier. So this is a cap. Okay, this is a cap, and this is a kind of cap, and then this is, so you just wear it. And then this is fit to your brain size. So if you order some shop, then there is going to be some size like your shirt, small, medium, large, and then these electrodes are positioned already and then stretched when you wear this. Okay, this is pretty easier, and these positions are named as international 10-20 position. or international 1020 systems. So there are names of each electrode: prefrontal, frontal, and these are frontal areas, and yes, there are occipital areas as well. Okay. And to measure EEG, you also need the amplifier or analog to digital converter. So these are, you see the two amplifiers and analog converter, and left one is of biosemi and right one is Laksa. And using this device, you can get the signal, EEG signals. And these signals, so I say this is the amplifiers because our signals, our body brain signals are so small, and we need the amplifier to magnify. And recorded signal is actually in analog at first, and to process in a computer, then you will probably need a digital converter. And yeah, these two devices were stationary, and these are used at the laboratories, and also there are some big machines for the hospitals as well. And they are pretty precise, it's like accurate, and there's also some mobile devices. These mobile devices are cheaper than the stationary devices in general, and this device is OpenBCI, and right one is the device of Neurosoft. I used to use this OpenBCI, and this is cheap. Yes, this is as you see, this is open. This is open, and this is not well maintained of the outside, but this is working well, and many research papers are using this device as well. So yeah, I like this one. Yeah, and yeah, Neurosoft, yeah, this is good as well, but I never used it before yet. Okay, and these mobile devices are good when you are trying to record the EEG, our brain activities, while during our real-time activities, like when you are moving outside, or when you are freely reading some books, and then these devices are pretty good because you can move freely with these devices. Okay. Yes, and this time let me talk about the signal processing techniques of EEG. Yes, as I just told you that EEG is a pretty complicated signal. There are so many channels, and then it's recording time is also very long sometimes. For example, if you have some problem in your brain, and if you go to hospital, and for example, if you have some problem of epilepsy, then you go to hospital and you are going to record your brain activities very long time, maybe 2 hours, maybe 3 hours, maybe it could be 24 hours. Yeah, it's pretty long, and size of the data is going to be very huge, and to analyze these signals is another job. So it's very, very difficult. Then how can you do it? So a very simple way is to train a doctor. And then he's reading this signal continuously. Maybe it takes time, 2 days, 3 days, or a week, but it's trying to read some specific patterns from here, but it's very, very difficult. So many cases, to understand this and to find some specific patterns, then many researchers use the frequency band analysis. Because it is possible, because it is known that some waves with a certain wavelengths are generated with specific activities. And for example, like if you focus on something, then probably you have heard that alpha power is going to be increased, or theta power is going to be increased. Then if you focus on something, or if you are trying to calculate some mathematical problem, then a kind of waves, specific wave, are going to be generated. And if you are trying to sleep or trying to be relaxed, then another wavelength, another waves with different wavelengths are going to be generated. So this is known, these facts are known to public, so we can use this kind of techniques of Fourier transform, wavelength transforms, or band power analysis, or spectrogram. The image of this is called spectrogram. So this is the x-axis is going to be time, and y-axis is frequency. So as you see, there are some strong signals at 1200 or 400 milliseconds. So this is not second, I think. This is going to be millisecond. And then, continuously. Maybe this is second, I can't sure. So if this is second, then this is going to be 10 minutes from the start. Okay. So this is very easy approach to understand the EEG. So still, and because this the easiness of this way of analysis, this method, frequency analysis, has been popular for a very long time. But in these days, because of deep learning, and many people trying to extract patterns directly and trying to develop an algorithm to recognize the raw signal directly. And this is one try. And okay, this is from my paper, and then trying to recognize some patterns from epilepsy patients. And when you have epilepsy in your brain, then you have some specific strange patterns in your brain, like a sharp. You see there are some sharp. So we say this is repeated spikes. And these spikes happens continuously. And in the third column, you can see there are sharp wave and then slow wave, and sharp and slow wave, sharp and slow wave. This kind of patterns happens. So to measure how bad is your brain, or whether to check whether your brain has some problems of epilepsy or not, then we can search these patterns from your brain signals. And also there are specific signal called P300, and this is the strong waves of 300 milliseconds after a stimulus. Like this is something like this. If something happens, like a ball is moving in front of you, then you didn't recognize it before, and suddenly it appeared in front of you and you didn't recognize it, and then suddenly you found that it is just in front of you, then you are going to be surprised, right? And then there's a signal occurs in your brain, especially your back of your brain, occipital region. And then this signal, there is going to be very strong response from the visual stimulus, and this is called P300 because this happens just after 300 milliseconds after your stimulus. And to understand these signals, to extract or to classify these signals, then these patterns, we can use many different methods, support vector machines or heuristics or just artificial neural networks, or in these days, deep learning is the most popular, and this is often to analyze and unknown patterns as well. Okay, and this is almost the end of this presentation, and let me talk about some applications of EEG. The first one is BCI, brain-computer interface. We are trying to control or command a computer with thinking only, with brain activities. Let me assume there is a game, maybe Super Mario or something, and basically, it's, usually we are controlling this character using a joystick or keyboard, but instead of that, maybe we can use our brain activities. And if we just think, okay, left, right, jump, and then it moves without saying, without speaking, but just thinking, then we can call this as a BCI, brain-computer interface. Brain-computer interface is a type of HCI, human-computer interaction, or human-computer interface. Then human-computer interaction includes all our body movements. So we can use our body gestures, or maybe just speaking. Then if we control the computer characters or environments, then we can call that as a HCI. And if you want to use brain, then it's going to be brain-computer interface. And this is an example of a BCI.
Machines with the human brain.
So you can see this surgery, and you saw it. Just they opened the skull and then put some electrodes on our cortex directly. Then yes, he can move robot arms using his brain activities. Also, he can feel the robot arms sensing as well. You can see this is connected, and then brain activities are recorded. And also, yes. Okay, here she is moving the robot arms to move an object. Okay, so this is possible. This is called BCI. But some students could be confused that, using BCI or brain signals, we can understand everything. It's kind of mind reading from the animation or something. But this is not. This is just reading very small aspect of thinking. The left or right, up, down, and close and far away. Or happy, sad. Okay, those simple and strong states of our brain, we can read it. But it is not possible yet to read the details of what you are thinking, what you are imagining. So that's not possible yet. Another application is I bring here is brain stimulation. The concept of brain stimulation is sending electric signals to brain. So just before you saw the video sending signals from your brain to the computer, but here sending signal directly to the brain. So why? To stimulate a specific function or parts of brain. So maybe your parts of your brain is not working properly, and then maybe we just give some stimulus, and we can give some signals, and then your brain starting to wake up. So we expect that, and then it works in somehow. It can be done on skin. So you can put some electrodes outside of our brain, outside of our skin, head skins, and then we can send some signals, and then to simulate it deep inside of our brain. This is possible, and also it is also possible to put some electrode directly to put deep inside our brain, and then give some electric signals. So this is used to cure some diseases like dementia. So there are so many people who suffer from dementia. So as we know this dementia is a brain problem, so we try to cure, many people trying to cure dementia using these techniques. So maybe it will help people who is suffering dementia. Okay. So it was a pretty short introduction of EEG, and I talked about the EEG, and then you understood that what the EEG is, and then probably you know that now. I wish you know that how you can measure EEG if you have a device, then how you can use the computer algorithm to develop a computer algorithm to recognize automatically EEG. And EEG applications, what kind of EEG applications we can have it. So I just introduced two things, is BCI and also brain stimulation. Okay. Thank you for your kind attention, and I will close my lecture here. Okay, see you next time. Bye.